Section 6.3, Day 2, Binomial and Geometric Random Variables. After today's lesson, you should be able to calculate the mean and the standard deviation of a binomial random variable and interpret these values in context of the problem. We describe the probability distribution of a random variable just like any other distribution by looking at the shape, center, and spread. Consider the probability distribution x of the number of children with type O blood in a family of 5 children. Remember from yesterday, the probability of having a type O child is 0.25. The probability distribution of x is skewed to the right. It is more likely to have 0, 1, or 2 children with type O blood than any larger value. The center, the median number of children with type O blood, is 1. Based on the formula for mean, the mean would calculate out to be 1.25. Based on our formula for standard deviation, the variance would end up being 0.9375, and therefore our standard deviation would be the square root of that, which would be 0.968. Fortunately, there's an easier way to calculate the mean and the standard deviation versus using the formula for a binomial random variable. Notice the mean, mu sub x of 1.25, can be found another way. Since each child has a 0.25 chance of inheriting type O blood, we'd expect 1/4 of the 5 children to have this blood type. That is, mu sub x would equal 5 times 0.25, or 1.25. This method can be used to find the mean of any binomial random variable with parameters n and p. Here are the formulas for calculating the mean and the standard deviation of a binomial random variable. Both of these formulas will appear on your formula sheets. Mu sub x will equal n times p. Of course, n is the fixed number of trials and p is the probability of success. And the standard deviation of x will equal the square root of n times p times 1 minus p. So that's the number in the fixed trials times the probability of success times the probability of failure. Note, these formulas work only with a binomial distribution. They can't be used for other distributions. Here's an example. Take a moment to read this about the activity found on page 340. So here I want to find the mean and the standard deviation of x. Since x is a binomial random variable with a parameter of n is equal to 21 because there's 21 students, and p is equal to 1/3, we can use the formulas for finding the mean and the standard deviation of the binomial random variable. Remember, mu sub x is equal to n times p, so 21 times 1/3 is 7. And the standard deviation is the square root of n times p times 1 minus p, or 21 times 1/3 times 2/3, which ends up being 2.16. So we'd expect about 1/3 of his class, meaning about 7, to guess correctly. And if the activity was repeated many times, groups of 21 students, the number of correct identifications would differ from 7 by an average of 2.16. The binomial distributions are important in statistics when we want to make inferences about the proportion of successes in a population. Suppose 10% of CDs have defective copy protection schemes that can harm computers. A music distributor inspects a simple random sample of 10 CDs from a shipment of 10,000. Let x equal the number of defective CDs. What is the probability of x equaling 0? Note this is not quite a binomial setting. So to perform the calculation, the probability of no defects, I would take 9,000 over 10,000 times 8,999 over 9,999, and so on, and end up with 0.3485. However, if I calculated it as a binomial distribution and found the probability of x equaling 0, I would use the formula of 10 choose 0 of 0.1 raised to the 0 power times 0.9 raised to the 10th power, which would be 0.3487. In practice, the binomial distribution gives a good approximate value as long as we do not sample more than 10% of the population. This is a rule of thumb formula that you need to have memorized. The sampling without replacement condition. We can use the binomial distribution to model the count of successes in the sample as long as the number in the sample is less than or equal to 1/10 of the number in the population. I, however, like to look at this formula a different way and say the population must be greater than or equal to 10 times the number in the sample. That can be found by just taking the original inequality and multiplying both sides by 10. Performing normal approximations for a binomial distribution. As the number in the sample gets larger, interesting things happen to the shape of a binomial distribution. The figures below show histograms of binomial distributions for different values of n and p. What do you notice as n gets larger? Notice how the p-value has stayed the same and the number in the sample has increased from 10 up to 50. Hopefully you noticed that the distribution became more normal. Suppose that X is a binomial distribution with n trials and successes of probability p. When n is large enough, the distribution of X is approximately normal with a mean and the standard deviation given by these formulas. Mu sub x is equal to n times p. Sigma sub x is equal to the square root of n times p times 1 minus p. As a rule of thumb, we will use the normal approximation when n is so large that n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. That is, the expected number of successes and failures are both at least 10. This is the second rule of thumb formula that you need to have memorized. So here's our final example for today. Take a moment to pause the video and read the example. So you can see here I want to estimate the probability that 1,520 or more of the sample agree. First off, remember I need to verify that X is a binomial random variable. Remember to check the bins. It is a binomial setting because a success is agreeing with it and a failure is to disagree. Independence, because the population of U.S. adults is greater than 25,000, it's reasonable to assume sampling without replacement condition is met. The number in the trials is fixed at 2,500, and the probability of success is the same for 0.6. Number 2, I need to check the conditions for using a normal approximation. So I need to check that n times p and n times 1 minus p are both greater than or equal to 10. And you can see when I take n times p, I get 1,500, and n times 1 minus p is 1,000. Both are at least 10. Next, I want to calculate the probability that X is greater than or equal to 1,520 using normal approximations. First, I need to find the mean of my probability distribution, which would be n times p, which is 1,500, and the standard deviation of my distribution, which would be the square root of n times p times 1 minus p, which ends up being 24.49. If I were to standardize this, remember it's x minus mu sub x over sigma sub x. Z-score value ends up being 0.82. So in finding the probability that z is greater than or equal to 0.82, I would use the z-table and find the probability that z is less than 0.82 and subtract it from 1. That value ends up being 0.2061. So what that means is there's about a 21% chance that I would find a sample where 1,520 or more agree. In tomorrow's lesson, we'll take a look at a new type of distribution called a geometric distribution.